And we're back. Welcome back and happy Thursday. Today we will continue on with our conversation about operating system structures. But before we begin, the reading consists of C Programming Essentials in 4 hours. It's a link to a YouTube video. Please look at it 20 minutes at a time, 15 minutes at a time, but please make sure you're making progress every day. The companion for that, I have paired PDF, C Programming Tutorial, that is to be your reference for the concepts that they go over in the video. They are both on the Blackboard, the course Blackboard. There's a new reading that I'd like you to get done by the 24th, a week from today, in the main text, OS Concepts, section 2.6 through 2.11. Pages 76 through 99. It's not a lot of reading, but you're going to have to make sure you engage the material every day, at least an hour per day for this class. Okay, so when we last left off, we talked about the compilation, the process for building a C program. You start with your C source, you compile it with GCC to produce an object file. You paste that object file together with the system libraries to form your executable. You run your executable and the loader brings it into memory, and if you specified dynamic linking, it also loads the libraries associated with the system calls and other services that your program uses. So let's continue on and look at OS specifics. Every operating system has a unique set of system calls. And so when you choose a platform for some system you're building, part of that application choice is the underlying system and operating system and hardware on which it's going to run. And these are essentially the services that are provided to the application by the operating system. And so because you have so many differences between operating systems, and there are many such differences, it's impossible to offer a single set of common application program interfaces. And so there are all sorts of choices for the human interface or user interface, perhaps even for touchscreens, the gestures that the vendor deems to be reasonable for certain sort of interactions, the way you do input and output, the libraries, things like 3D camera, or maybe the ability to render graphics, augmented reality. There are also other choices for the binary interface, how you run and execute programs in their binary form. There can be many different binary formats. You can also circumvent a lot of these issues through interpretation. With an interpreter, you can have the same program, as it were, on different platforms. But underneath the covers, inside of the interpreter, you're going to have to implement all of the runtime semantics or behaviors for that particular operating system, that particular language platform. So let's take a look at design and structure. And therefore, the design and implementation of an operating system is not really solvable. And what do I mean by that? It's not a single solution that works best for what it means to be a quote-unquote good operating system. In reality, the question that you ask yourself is, do the services available on this operating system satisfy the goals that I have for my application? So the first thing you do is you start by looking at the goals and specifications of the underlying platform or application that you have. What are your needs? And this is affected by multiple things. At the bottom, the base level, it's impacted by the type of hardware you have available. And so let's say you have a piece of hardware that has a custom chipset that can do very strong encryption. Well, certainly that machine, when you're building encryption services, you're going to be able to do more on that machine than something that only has a very modest processor and no specialized hardware. And so you start by looking at the goals, but these goals are tempered by the capabilities afforded by the underlying hardware. So the internal structure is different for every operating system. It can vary very, very widely, and there's no one way of building an operating system, but certainly we look at strategies and we look at components and we look at the behaviors and the relationship between the applications, the devices, the operating system. And so We also have user goals and system goals. And so for a user, you might want an operating system to be accessible, convenient to use, or maybe it's easy to learn. You don't have to read through thousands of pages of manuals in order to do basic things on it. It has to be reliable. Every time you go to use it, it's there, it works stably, repeatedly, without fail. It has to be safe and fast. You don't want things to take too long, but you also don't want it to do all sorts of things with the information that you might not perhaps want to share. Goals of the system is that it should be easy to design and implement, because certainly over time you're going to want to have to change it a little bit here and there. It should also be flexible and error free, as well as efficiency, because people spend a considerable amount of money on this hardware. You want to make sure you're squeezing out every bit of capability out of the underlying hardware as you possibly can. And so another aspect of your design and implementation of operating systems is this importance between, or this dichotomy between so-called policy and mechanism. And so the reason why you separate policy from mechanism is because sometimes you want to change either the way things operate or how the implementation plays out in the implementation of some sort of operation of a component of your system. And so this idea of policy states about what will be done. So for example, if a process is executing on the processor and it has been running for quote unquote too long, what will be done? Well, that policy is once it's been running too long, it's going to be kicked off the processor, let's say after 10 milliseconds. That's a policy issue or solution. Now, mechanism is how physically does it kick things off the processor. The mechanism is it takes a data structure that represents the process state, it copies it from the various components like the register file, stack pointer, memory pointers from the CPU, and then once it populates it, it writes it into memory or it writes it onto disk. That's a mechanism. It's the implementation of that what will be done. That's the how part. That's the mechanism. And if you separate these two concerns, policy from mechanism, you can always change the amount of time, for example, after which it kicks a process off for a processor. And you can also change how it actually does it. Sometimes it might store that data structure in RAM, other times it might store it on disk. And so by separating these two concerns, you have much more flexibility in maintaining, upgrading, and possibly tuning your operating system implementation as it goes forward. And so the mechanisms, as we said, define or determine how to do something. The policies are what will be done. And the separation between the two is very important because it makes it flexible. And things that are flexible can be changed and also can be customized to many different applications. And so when you specify and design an operating system, it's a very creative task. And in fact, there are two things that will really make you an expert in data structures and algorithms, and that's to work on the internals of an operating system or to work on the internals of a compiler. I highly recommend it. And in this open source era, the source code is freely available to you to dive in. Jump in the water is fine. And so implementation, there's a lot of variation. And the early operating systems had a lot of assembly language. Now, assembly language does not hide the details of the CPU. It's a high-level version of the CPU's native language, and it requires you to know a lot about CPU and computer architecture. So then after that, you had programming languages for systems, things like ALGOL and PL1. And PL1 was the precursor to Pascal, which is no longer used, but at one point, maybe about 20, 25 years ago, it dominated in the undergraduate computer science curriculum. That was always the first language you learned way back in the day. But nonetheless, now C and C++ are the quote-unquote systems languages. They give you low-level access to the machine, and you'll find that out in the programming assignments that we're going to have throughout the semester. And you also have a mix of other languages, more high-level languages these days, things like Python, Perl, Java, and so forth. And so you usually have a mix of languages that comprise the programmatic interface to your system. The lowest levels are in assembly, but the main part of your operating system is typically in something like C or C++. Now, you often have systems programs, these utilities that are useful. These things can be in more high-level interpreted languages like Perl and Python or shell scripts, but generally a lot of them can be in C and C++. The higher level languages afford you the easy ability to port or to bring this application to another platform, but the trade-off for that flexibility is that it's a lot slower. Now, with emulation, you can actually, in a binary level, you can mimic the execution of a different operating system on yet another operating system. Now, this gives you a slowdown, but oftentimes in real terms or in the real world, when someone invests a lot in an application, just because the operating system changes, they don't want to throw out that investment. And it's not just the cost of the software we're talking about, it's also the cost of all the training for an organization. So imagine if you had an accounting business and you had 100 accountants working for you, and over time it took you a lot of time and effort for them to all be trained on the accounting software. Now, all of a sudden, if the platform changed and no longer supported that software, well, it's going to take you another year or two at high cost, both for time as well as money, to retrain everyone for the new system. And so this emulation is really, really important for maintaining a migration path, as it were, for old applications to continue to be used as aspects of the operating systems change. And so a general purpose operating system is typically very large, and the operating systems that you've come to know, like Mac OS 10 and Microsoft Windows, they're trying to be everything to everyone. And because of that, there's a lot of code and a lot of services stuffed into it. And these general purpose operating systems, for this reason, are often very large programs in general. And so when you install an operating system, it takes tens of megabytes, easily hundreds of megabytes to install it, because there's a lot of code and binaries required to serve all those many different purposes people might have for these operating systems. And so there are many ways people have come up with over the years to structure the software for an operating system. There's simple structures like MS-DOS. At the time, for when MS-DOS reigned supreme, there was nothing really else out there, and DOS itself was, the hardware was a lot simpler, so they could kind of get away with it. Unix was more complex, and then after that followed a layering approach, and it was a way of presenting various components of the system in an increasingly protected, higher level set of interfaces. And then we have microkernel, which took the components and kept the kernel very, very simple, and then all those services that would typically be part of an operating system, like the file system, process scheduling, it was a call out to some service that used a communication mechanism. And so here's MS-DOS, and MS-DOS was written to provide a lot of functionality in very little space. And when you try to kind of mush all of that functionality into a small space, you don't do a lot of very good abstraction, and you just have one big body of code. And so MS-DOS, for this reason, was not divided into modules. And although it had a little bit of structure, all the interfaces and all the different functions for different aspects of interaction with the system and the user, they're not very well separated. It was just one big ball of code for the most part. And so in this schematic, and this is the book, it talks about the relationship between the various components. You had the ROM, BIOS, device drivers that talk to the hardware, so this hardware abstraction layer type of thing for MS-DOS. And then you had the device driver for MS-DOS that interacted with the BIOS for the individual pieces of hardware. And then you had resident system programs, so these are the programs that would stay in memory and they would perform things for you. And then on top of that, you had the application program. So this was MS-DOS. It was pretty simple, but it did its job quite well for the time being. Now, Unix was limited by the hardware functionality. And in the beginning, Unix had no structuring, but over time, it started to get some structure. And so the biggest contribution that Unix made was having two separable parts of your software. You had the so-called systems programs, those utilities, those runtime services that I alluded to in a previous module. And then you also had the kernel that was the heart that did all of the coordination of the parts of the system. And so the kernel was everything below the system call interface, but above the physical hardware in the first versions of Unix. And this kernel was responsible for providing file systems, CPU scheduling, memory management, and other types of functions. And it had a large number of functions all at one level. It didn't subdivide it in the early days. And so this was a very important thing, because now it meant the basic operation sharing of the parts of the hardware to those who wanted to use it was separate from the abstractions or services made available that applications might want to use. So, for example, if you're going to do media streaming, you take data off a disk, and then you pull it into RAM, and then you send it through the I/O controller to the network card and off the network. Now, certainly, you can implement a bunch of system services, specifically called the media streaming APIs, and these are going to make use of the different system calls made available through the kernel, some of the kernel services. And so this was a very important separation, if you will, because it meant that you could continue to grow the repertoire of tools that the system could perform, or the system had to offer, without modifying the underlying coordination of the hardware that the kernel gave rise to. And so this is an example of what the kernel is. Below the kernel, we have the interfaces to the hardware. Above the kernel, we have all the different interfaces, and we have the system libraries. So what did the kernel do? It did things like swapping in blocks of data to the buffers and from the buffers for the I/O devices. It looked at CPU scheduling, the ushering on and ushering off of the CPU of programs that are executing instruction streams. It also had this management of the file system, the presentation of a contiguous tape of storage as a linked list of blocks laid out on sectors and tracks of the disk, a linked list of them. And so the kernel performed all of these, and then the applications above and the interfaces, anyone who wanted to use these would then make a call to the kernel through the system call. And it was the kernel that did this work on behalf of the user application. And so the layered approach is akin to that, but it had a number of different levels of abstraction. And so it was called layered approach because it had a bunch of quote unquote rings, and each ring represents a set of functionality that corresponded as you go closer and closer to the center to more critical types of low-level access. And so the operating system itself was divided into a number of layers, and each was built on top of one another. Now, this is just the basic software engineering abstraction mechanism. The bottom layer itself, layer 0, was the hardware, and then on top of the hardware was something that would abstract the hardware, and then on top of that abstraction, layer 1 would be layer 2, which took those hardware abstractions and implemented control programs to allow you to do sophisticated things with those pieces of hardware. And again, as you go out and further out in these layers, you would reach that final layer, N, which was the user interface. And so this gave you modularity, and each of the layers are selected so that each one uses functions and services at the seams between to the layer below it. And so this is a basic software abstraction mechanism, and what it meant is that you can change the details of what it means to implement the file system, or what it means to do memory management, or what it means to lay things out on the platters of a disk drive without disturbing the software or the programs that made use of those services. So it gave you this clean interface and a way to customize and really change and alter the implementation capabilities of the operating system without disturbing all of the services above that layer that made calls to the API interfaces at the seams between layers. And so lastly, the microkernel architecture. The most famous example of that is something called the mock operating system. And it operated on the principle of simplicity means speed. And so as much of the complexity as possible for doing things like memory management, process scheduling, was moved from the kernel into the user space where the applications run. And so the kernel was only responsible to do very, very basic things, and you could make it really simple and therefore very fast. But whenever the kernel needed to make a scheduling decision, for example, for a process or a thread, it would call out to these services in user level space. And this required message passing between the kernel and that user level service. Now, this message passing meant that you incurred a slowdown whenever you were going to do an operation. But there was great benefit to this, that it was much easier to customize and extend and change the behavior and add on to what a kernel could do. So for example, in a microkernel architecture, if you didn't like the process scheduling because it did not suit or benefit real-time applications better, well, you could write a different scheduler, plug it in, And now you would have your operating system, because it has a microkernel, you can plug in a new scheduling algorithm. It meant that now you could change it or extend it to benefit streaming type applications or real-time applications, for example. This also made it easier to port the operating system to a new architecture. So all you had to do was just change those portions of the kernel that interacted with the hardware, and those services like memory management, process scheduling, and so forth, they would stay the same. They use the interfaces of the kernel, so the kernel was much simpler. It's more secure and it's more reliable because less code is running in the kernel, and things that are very small and very simple tend to perform much better without error and certainly with increased speed. So this is an example of a microkernel. Down below. We have the hardware, and that hardware interfaces with the microkernel. And so if you swapped out and went to a new architecture, hardware architecture, you just have to change whatever those interfaces are for the APIs between the microkernel and that hardware or those hardware services. And so up above, we have application programs. We also have our system programs. So in essence, what a microkernel did is it took the runtime services that otherwise would have been in the operating system and made them individual services that you just pass messages to back and forth in order to perform certain type of applications. Same thing for device drivers. And so the microkernel had some basic operations. It had the ability to do inter-process communication, to send messages between processes, because that basic functionality is needed because the microkernel relied on those services for some of the functions that it needed to coordinate resources for the underlying hardware. It also had memory management. Well, that was a basic thing to be able to usher programs into memory and take them out of memory and put them on disk. It also had CPU scheduling implemented. Now, of course, the scheduling algorithm could certainly be a call out to a service, but the basic scheduling for how you start a process and stop a process, that functionality was in the microkernel. And so the kernel code consisted of a small number, very basic operations, but everything else was a user level service that the kernel interacts with through the message passing. Okay. So a lot of this idea of pluggability was carried forward into this notion of a module. And many modern operating systems recognize that while the system is running, you might want to replace the way it's laying out the file system or the strategy for scheduling, for example. And so they developed this kernel loadable module, and you can almost imagine this like a shared object. We talked about this idea of dynamic linking and dynamic loading. Well, a loadable module is a similar concept, only it's for the kernel. Now, this uses an object-oriented approach, and each of these modules is literally a library of functions for some particular purpose used by the kernel. And each component is separate, and it talks to the others over specific and known interfaces. And these loadable modules are loaded as needed within the kernel. And so if they're loaded when needed, if you want to install a new strategy for scheduling, all you do is you unload the existing module, load a new module, and then resume the kernel. And in many cases, you can actually change this new module, and then the moment your kernel is done with that operation, the next time it reloads the new module you've installed, and it just continues seamlessly. And so this is similar to layers, only you're using these modules that you load and unload instead of having these concentric rings where you have these APIs you access at the seams between outer layer and inner layers. And so Linux and Solaris are popular examples of kernel loadable modules. And this is an example of the Solaris architecture. You have the core Solaris kernel services, and you have classes or loadable modules for things like scheduling, implementation of file system, implementation of executable formats. And this one is very interesting so that you could add support for the Solaris kernel to be able to run programs in different binary formats simply by extending these modules. It's a very interesting operating system. This is not all hard and fast as a rule, but you have very many hybrid approaches. And so most modern operating systems, they're not just one pure microkernel or kernel loadable modules or ring-based or layered. They often combine many of these together. And so multiple approaches address certain things so like scalability, things like security and protection, usability, and so forth. And so, in particular, Linux and Solaris, their kernels were in the kernel address space. They were monolithic, so everything was in one ball. But they also used modules for the dynamic loading of certain aspects of functionality. So it kind of looked like MS-DOS in one sense, but also looked like module kernel loadable modules in another sense for only certain types of operations for the Solaris and the Linux kernel. And so Windows is mostly monolithic, but it also uses a microkernel. So this idea of services for certain types of operations. And these operations are subsystems called personalities in Microsoft Windows. And then Apple uses a hybrid for OS X. It's layered in one part, but it's also uses microkernel parts of Mach for certain operations. It also uses them for things, certain other services like the I/O kit. It does dynamically loadable modules, and in Mac OS world, it's called kernel extensions. And so this is the Mac OS structure. You have the I/O kit, things like kernel extensions. You have the BSD-like portion, which is a microkernel. You have the Mach-like portion, providing you kernel services. And then you have application environments and services, things like Cocoa, and you have the graphical user interface, the Aqua graphics set. iOS is a version of Mac OS, but you have added functionality, system runtime services for the things you'd see on your mobile device like your iPhone or iPad. So it runs applications, but also runs on different architecture like ARM, Advanced RISC machines, and more recently, Apple has its own A13 processor, their own silicon. And so certain things on iOS are additional to what you'd see on Mac OS, but it's tuned services for the hardware that you have, those differences for mobile device hardware versus the desktop and laptops, as well as being able to run on different chipsets. And so Cocoa Touch is an API in Objective-C. It's an object-oriented language. It does media services, core services for things like cloud computing, the iCloud services, as well as the core operating system stuff is based on Mac OS X kernel. And so iOS is an amalgam and a prime example of how you take the basic kernel and you extend it to work with all of these other hardware resources that you need or have on your mobile device. Android was developed primarily by Google. It's open source, and it's similar to iOS in that it's a customized version of Linux kernel with all sorts of runtime services to serve the needs of the mobile hardware devices. Android also has applications, runs Java applications as the application binary interface. And so Java class files are compiled down to Java bytecode and then it's translated to execute in something called a Dalvik virtual machine. And so you have all sorts of libraries available, WebKit, SQLite, multimedia stuff, as well as a smaller version of the C runtime library, libc, to execute C programs as well. And this is the Android architecture. You have your application frameworks. You have your libraries for doing things like OpenGL for graphics and multimedia. You have the runtime, which are your core libraries, plus a virtual machine for running your Java. And Java is the application format of or language of choice for Android. And so let's take a look, lastly, at building, booting, and debugging. So debugging is really, really important in operating system design. Oftentimes, things will go wrong, not necessarily a crash, but things will go awry as a course of running or in the course of running your operating system. And so debugging, of course, is the finding and fixing of errors or bugs. And operating systems often generate log files. These log files are little messages they write down to tell you the status of certain things that they're doing, like printing and scheduling processes and other such things, interacting with the file system and so forth. And so these log files will often contain error information, and there are lots of tools out there that allow you, the user, to interrogate or examine the contents of these log files in order to diagnose what's going on, what is the status of the operating system as it's running. So this is used quite a bit in performance tuning, but it's also used for detecting errors as well. When an application fails, it can generate something called a core dump. It's basically a capturing of memory of the process, how much memory it had, what it was using, what it was doing when the crash happened, when it exited. If you've ever been on Microsoft Windows or on Mac OS and an application exit, you get this pop-up window that says, shall I send this to Apple, for example? If you look at that, that's an actual core dump, and it has a snapshot of the CPU registers, the memory pointers, and a snapshot of all the state associated with your process when it crashed or when it exited. And so an operating system failure itself can generate a crash dump file, and that contains the kernel's memory that it was using. And so when an operating system fails, it means that your system freezes up and something went really wrong with your OS. But this memory reporting, this debugging information is also available even for the operating system, not just the applications that run on the operating system. And so beyond just the crashing, this log information is very important for performance tuning to ensure that your system is running efficiently and as quickly as possible. And so there are listings of activities called traces that some operating systems make available. And there's another thing called profiling, which is the periodic sampling of the instructions that are being executed. And for profiling, you're looking for statistical trends to see, oh, where is my operating system spending much of its time doing the normal things that it does. And so, for example, if you find that your operating system is accessing the disk very frequently, it might mean that you have too little RAM because it can't squeeze all those programs into memory, so it's taking the spillover and storing them on disk, and it's using the disk more than it should be. And so Kernighan's law says that debugging is twice as hard as writing your code. So therefore, write it well as much as possible. And if you write it well, you're not really going to need to debug. But people argue that debugging is harder. So if you do your best work in your coding, that means you're not a very good debugger. Go figure. In performance tuning, a lot of this accounting information is made available to you in this picture. We have the Windows Task Manager, and what this tells you is how different processes that are running, how much of the CPU they're using, and other metrics like memory and things like that. And so the reason why this is available, because it can help you to improve your performance by improving those things that are the bottlenecks slowing down your system. And so the operating system has to provide a way for you to display these measurements of system behavior. On Unix, the command top will give this information to you, but on Windows, the Task Manager will allow you to list all of the programs or processes running and look at things like how much memory they're taking, what percentage of the CPU they're taking up, and so forth. And so in Solaris, there was a tool called DTrace, and what DTrace allowed you to do is literally track all of the function calls, even if it was a function called a function that are traversed when you're executing certain operations. And so you have a probe, and this probe would trigger based on a particular operation you're performing, and you could write custom code to save some information, and it'll also give you text printouts like this printout on the right that lists all the function calls. And so here, where we have a right-hand arrow, that represents a call into something, and where we have an arrow pointing to the left, that's a return from some function. And so here, it lists all of the functions called starting with X events queued. That's for X Windows. And so it calls underscore X events queued. X11 is a version of X Windows. IO control, so you're looking at file descriptors, you're calling getF, and it shows you literally a listing of the trace of all the functions that were called, leading from starting at a particular event. This was immensely useful for debugging. In particular, as your system grows more complex, it's nice to actually have a visualization of what's happening in your system. And so for DTrace, you could specify certain trigger functions, and these trigger functions will get called out, and you could store information that you could get back or print out or log as a result of performing some operation. And so this particular DTrace fragment will record the amount of time each process with a certain user ID spends running on the CPU. So you could say, oh, well, you'd enter this code in, this script, and to the DTrace system, you'd write schedule.d, this might be schedule.d, and then you'd say DTrace, and you give it the name of that DTrace file. And so then, whenever user ID number 101 would get scheduled on the CPU, you could actually record the amount of time it's spent on the CPU. So this gave you a custom method for doing debugging of the interaction between operating systems, in particular, in this case, Solaris, and all of the programs that use that operating system. So it allowed you literally to write your own instrumentation of how the kernel was being used by the programs that were running on Solaris. And so operating system generation, they're designed, operating systems are, to run on a number of different machines. And oftentimes you take this code base, you compile it, you specify different options based on what aspect of an OS product you wanted to compile and build. And so there was typically something called sysgen, and this program would go off and it would collect information about your hardware and then generate a bunch of variables that you use to select certain aspects of your operating system so that when you compile it and link it and generate the executable of the operating system, it's custom built specifically for the hardware resources that you have. And so this makes it much more efficient because it's an exercise in futility to actually compile all of the operating system. Because inside of an operating system, you have a lot of components. It strives to be general, so you don't need all the components. You only need just those components specifically for the hardware that you have. So when you compile an operating system, there are many operating systems that allow you to generate from the code base exactly what you need, making it much more efficient. So if you were going to develop a server application, I would recommend you do an OS generation, the sysgen, rather than just use the general purpose operating system. So, for example, if you're writing a server that's going to be a high performance database server, well, you don't need the word processor and the spreadsheet and all that other software. You just need those components for the fast file system, for memory management, and I/O transfer. You don't need all the other components. And so a sysgen would help you in building a system specifically tuned to be a database server. And so when you turn on the power on your machine, the system boots. And power is initialized. You have firmware, which is non-volatile memory, and it holds the initial boot code. This initial boot code has Bootstrap Loader, and it looks to load and execute something. And so it will load the kernel into memory, and it starts the kernel from the kernel's main routine. But there's sometimes a two-step process where it looks to the boot block of fixed location and in ROM, read-only memory, and it loads the Bootstrap Loader, and this Bootstrap Loader resides in a specific location on disk, and it'll present you a menu of all the operating system choices that you can load. In fact, Grub, which is a Linux-ism or GNU-ism, is a popular Bootstrap Loader, and sometimes in a virtual machine, when you load it, and you'll see this with the VM that I'll distribute for this class, it'll present you a menu of choices of different operating systems to load. This is Grub. It's that second approach using a so-called Bootstrap Loader. And so once you select a kernel, the kernel loads, and now the system's running, and it's listening and waiting for requests from the applications and from the user. And so this is all I had. We'll end there. Please make sure you're keeping up with the reading. As usual, have a great weekend. Stay healthy and stay safe.